All right, we'll get started in just a second or two. Again, we're picking up with chapter 6. The notes are online. And we'll get started in just a minute or two. Again, a reminder as well, if you have questions, feel free to type them in the chat box. All right, let's get started then. A couple of things, as you might have saw, hopefully in the announcement, the exam is going to be not this Wednesday, but it will be the following Wednesday. But this Wednesday, we will be having a quiz, and we will be having a quiz again on nomenclature, which I believe covers chapters 3 and 4 a little bit. So all nomenclature will be on the quiz. That includes type 1, type 2, type 3, polyatomic ions, and I think we talked about acids as well, so that would include that as well. Well, we're going to be taking that on this Wednesday, which I guess is the 23rd. We will have lecture on Wednesday, so we are going to lecture, but we're just going to end lecture a little bit early, and that will hopefully free you some time to take the quiz. I don't anticipate the quiz going to be very long or anything like that. So that should hopefully, you probably, if you take it when we stop lecture, probably should be okay for lab and all that. If you do have lab on Wednesday, that shouldn't take, I don't think, that long for you to take the quiz. All right. So hopefully you had a good little rest from live lecturing and all that good stuff. I did post up just in case you haven't seen it, but I hope you have a few lectures on chapter 5. Again, they're recorded lectures for different parts of chapter 5. Make sure that you do go, obviously, and watch those if you have not watched them already, because the exam, which will be again 1 week from this Wednesday, we'll cover through chapter 5, I believe. So that'll also give you a little extra opportunity to watch those videos if you need to. And also, if you do have questions, obviously you could contact me, send me an email or something like that. I'd be happy to answer any questions that you may have. So we're going to start here today with chapter 6, which again will be on the next exam, which should be exam 3 at that point. And it's going to be about energy. And again, these notes are up online if you haven't found them already, where they are normally located in the module with the all the rest of the notes there. All right. In terms of the homework as well, I probably will adjust the due date for the homework until next week. The online homework as well. I just haven't had a chance to do that either. Okay, so off to chapter 6 here. We're going to talk about energy in this chapter. We're also going to talk about some equilibrium, a little bit about Le Chatelier's principle, but let's start with energy. So energy is the capacity to do work. There's different types of energy that we come across. There's potential energy. So that potential energy is basically what is sometimes referred to as stored energy. There's also kinetic energy, which is the energy due to motion. Again, sort of classic with that, a little bit what we talked about, I think, previously. So, the potential energy is that classic sort of giant boulder on top of the hill there. It's a big boulder. It's a very big boulder. Let's try that again here. I went a little crazy. So we have that big boulder on top of the hill. Again, it possesses a certain amount of energy due to just really its position. Obviously, if that big boulder falls over the hill, it will then kind of transfer energy to kinetic energy, which is the energy of motion. Again, if it hits the ground at some point, then it will actually transfer this energy from kinetic energy back to potential energy. And it will come to rest at sort of a different energy level. And a lot of the energy that we talk about and sort of the idea of energy, especially in chemistry and so forth, is that idea of the law of conservation of energy. It basically states that the total amount of energy of a system doesn't change. You cannot create nor destroy energy, but you can, sort of the example there with the big giant rock, you can transfer energy from one form to the next. So as that rock starts to fall, it's going to go from potential energy to kinetic energy. And then obviously once it hits the ground down here, oops, back here. So once it hits the ground down here, it would obviously transfer all that energy of motion, which is kinetic energy, and come to rest with a different potential energy than it did when it was up on top of the hill. It would also transfer all that excess energy into, say, the ground. And then, so we wouldn't lose any energy. It would just be transferred from one form to the next. So when we talk about energy, there's also energy that is sort of stored within bonds, and bonds have sort of potential energy that's stored when we make bonds, and when we break bonds, there's a certain amount of energy associated with those processes. And as we'll see in this chapter as well, when we talk about sort of energy as a whole, when we talk about energy as a whole, there really is two types of energy that we talk about, and one is exothermic. That's not working so well today. So exothermic sort of reaction. And we have an endothermic reaction. Try to write it the old-fashioned way here. And really the difference between these two is exothermic reaction is when heat and energy is being released, and endothermic is when heat and energy is being absorbed. And when we have bonds, when we make bonds and break bonds, there's a certain amount of energy that's either gained, which is or absorbed, which is endothermic, or there's energy that's released in that process, which is exothermic. So the whole point, sort of, as compounds are being formed, is compounds that have a lower potential energy is more stable than things in higher potential energy. And that's the basis of all energy, is essentially things are always sort of more stable and more happy in a lower state of energy. And reactions that have products with a lower potential energy than the reactants are favored. Again, the idea of the reaction is to get everybody into a sort of better state of energy, if you will. And again, that's a more sort of lower state of energy in terms of potential energy. And that really does favor a reaction to take place. When we sort of end up with sort of higher energy and stuff like that, it's not necessarily sort of favorable for that reaction to actually occur. So I think we went over some of these units earlier in the semester, but just in case, let's just kind of cover some of these things. These are some important sort of units that we oftentimes will see with energy. And one unit that you commonly will see is a calorie. And a calorie is basically the amount of energy that's required to raise 1 gram of water by 1 degree Celsius. And a very common sort of unit that's related to that is joules. And a joule and a calorie are two very sort of common units that are used. And this is an important sort of relationship as well in terms of uh, the relationship between a calorie and a joule. And that's a conversion that you'll sometimes do a lot in chemistry, especially when you start doing some calculations that involve energy. 1 calorie is equal to 4.184 joules. This calorie with the lowercase c is the calorie that we associate with sort of energy. It shouldn't be confused with the C that's a capital C. Capital C calorie is nutritional calorie, and you'll sometimes see that as well. So um, typically in energy, in terms of calories, it's the lowercase c that we use. If you see the capital C, again, it's a nutritional sort of calorie, but we talk about more with food calories and those type of things. Also, common units of both of those calories and joules is sometimes they are converted into kilocalories and kilojoules. And a kilojoule or a kilocalorie is just really the metric conversion of 1,000. So there's 1,000 joules in a kilojoule. There's 1,000 calories in a kilocalorie. So those sort of 4 units are ones that you see a lot in chemistry. As you continue on, you'll actually see more of the joules usually and the kilojoules. There's a lot of the units that you'll see the most often when we sort of talk about energy. Speaking of which, this is down here. Let me get this maybe right correctly. I'll try this. A big calorie with a capital C, like I wrote there, is again a nutritional calorie, and that is equal to 1,000 of the little calories. And again, that's equal to 1 kilocalorie. And if you're ever on the treadmill, you'll sometimes see where it says calories. It'll actually say sometimes kilocalories. And again, at 1 kilocalorie, which is 1,000 of the little guys, is equal to 1 nutritional calorie, which is what the capital CAL refers to. So let's talk a little bit about sort of bond making and bond breaking and sort of the relationship that occurs in terms of energy. So when molecules come together to react, bonds are broken in the reactants and new bonds are formed in the products. So when we're talking about sort of a chemical reaction or some type of process occurring, again, our products are on the right-hand side of the arrow. Our reactants are on the left-hand side of the arrow. And if the difference between all the bonds that we break and all the bonds that we make will give you for the overall reaction sort of what's happening in terms of the energy. So let's take a look here. So when we to break this bond, for example, here, to break this bond and breaking bonds, it's actually a endothermic process. So when you break a bond, it's endothermic. So this is endothermic. And that means that heat and energy, basically, our energy has to be put in. When it puts in, this guy over here, he gains a lot of energy. This guy on this side also gains a lot of energy. And when they do that, they basically have enough energy to break apart from each other into their individual components. So again, when we talk about bonds being made, bonds being broken, when we break bonds, apologize for the pen, it's a little out of control today. a big term. um, it's apparently not very happy today. Let's try that again. All right, let's see if we can get this way better. All right. So when we, again, break this bond, it's going to be endothermic. So in this particular case, to break a bond, and when you break different bonds, as we talked about when we were talking about with bonding, a double bond is a lot more energy to break than, say, a single bond. When you have a triple bond as well, it's a lot more energy to break than a double bond. So remember that. And when we talk about bonds, single bond is sort of the easiest to break in terms of energy. Double bond, a little bit harder, and triple bond would be more energy. And we would have to put 58 kilocalories per mole here. And usually when things are endothermic, it usually is signified by a positive value. So sometimes people will say this would be positive 58 kilojoules or kilocalories to break this bond. Now, the opposite is true when we have to make a bond. When we're making a bond, what happens is, again, these guys are, moving around a lot, and they have a lot of energy. So they actually have to sort of release energy. And when they release energy, that's, again, more a exothermic process. And heat and energy is released. And when they do, you can kind of think about the idea that they maybe slow down a little bit. They're not moving as fast. And that's going to allow them basically to sort of come together here to make the bond, like what we see over here on this side. So as they lose that energy, they're not sort of vibrating as fast. They're slowing down. It allows them not to have enough energy basically to, kind of miss each other. So they were able to come together basically and make that formation. So when we make bonds, it's exothermic. And in reality, this number here is the same amount of energy, regardless in this case. For example, if you're making a Cl bond to a Cl, or if you're breaking a Cl-Cl bond, it's actually the same number in terms of energy. And again, that's the idea of conservation of energy. It doesn't take any more energy to make the bond than it does to break the bond. The only difference is sort of what's happening with the energy. And in the case of making the bond, like on the middle of the screen, that is going to be endothermic. So the way that we represent that in terms of numbers for energy is it would be a positive number. While on the bottom of the screen, that is making the bonds, which is going to be exothermic. And again, the way that we represent it is by the negative symbol or the negative sign there for the energy. So that conservation of energy, again, is really a basic idea if you want to kind of think about the conservation of energy. We have a system, whatever that may be. We have the surroundings, which is everything outside of that system. And the idea here is as energy flows from one way to the next, it's basically equal in terms of the energy. So if we're talking about the system in this case, it would be exothermic. So the number would be a negative number that comes out, while if we're talking about sort of the system coming the other way from the surroundings, it would be a positive number kind of coming in. So the number that goes out, the number that comes in, and all these sort of processes to do with energy is always going to be sort of the same number. Again, it's just really the sign to indicate whether it's an exothermic process, that energy being released, or an endothermic process, that energy being absorbed. So as I mentioned before, one way that we sometimes do sort of represent energy is with this symbol here, which is our delta H. And our delta H is what is known as the enthalpy change. And basically, we could do a delta H for an overall reaction. We could do a delta H for, excuse me, for sort of individual things. But basically, you think about it as sort of the heat of a reaction. And delta H is a lot of ways in chemistry how you sort of see energy displayed in a reaction. And the delta H as well, it is used kind of the same way to demonstrate either endothermic or exothermic. You could do this for an overall reaction. So if you take all of your products and you take all your reactants and you want to do it for energy. So basically on the reactant side, what happens is we have to break all those bonds. And on the product side, what we have to do basically is make a whole bunch of new bonds, right? So it's really a process of breaking and making in terms of energy. And basically the difference between all the energy required to break the bonds and the difference with all the energy required to make the bonds will give you for that reaction the overall delta H. And again, that delta H may be a positive number. And if you get a delta H value that's positive, for most purposes, what you'll do in chemistry a lot of times is the number is not all that important in a sense. It's really just a sign that you see. So as soon as you see a delta H value that has a positive sign, you automatically know that that process that you're looking at is going to be overall a endothermic process, which means heat and energy is going to be absorbed. And same idea if you see something where the delta H is negative. Again, in a lot of cases, the number not truly sort of important for our purposes, but really the sign is important there. So if you see that the sign is negative as well, again, that's going to mean that overall that process is exothermic and heat and energy is being released. And that's what we see down here. Again, the process where we would break this bond is going to require actually positive 58 kilocalories per mole. And again, that positive number, regardless of sort of what the number is, but as soon as we see that positive number, that's exactly how we know that this process is endothermic. We have to put heat and energy in. Just like over here, if we did the opposite to make this bond, it would be minus 58 kilocalories per mole. And again, strictly from that minus sign, that's pretty much all we need to see to know that this is going to be a exothermic process. And again, delta H is a very, very common way that energy is sort of displayed to you, or a way for you to recognize in a chemical reaction, is it exothermic or endothermic? And essentially they'll just give you the reaction like they do here with the actual numbers, and pretty much at the end of it, a lot of times they will just give you the delta H value. And again, you can look at it for our purposes, really the number not super important, and you'll either see it being positive or you'll see it being negative. And again, from that, what you'll be able to determine is exothermic or endothermic in terms of the reaction. Any questions on that? Again, if you do have questions, feel free to type them in. Even if I maybe pass where we're at, I will go back there and obviously answer your questions. So when we talk about bond energy, this is sometimes what is referred to as bond energy when we talk about making and breaking bonds. Bond dissociation energy, or just straight up bond energy is sometimes referred to. And when we calculated sort of for the overall process, we basically divided it into sort of two parts, the making and the breaking part. And again, here's another example. If we wanted to break this bond between the two hydrogens, again, we would have to put the energy in to do that, which tells us it's endothermic, this process, and that will break apart these two guys into its atoms, essentially, which essentially means in a reaction, these guys are now free to go off and, you know, make new bonds and form new bonds on the other side. And we can see here the opposite is true. These guys need to give away energy or lose sort of energy. And as energy is being sort of released, again, we see it's the same number because it's the same bond. But again, in this case, it would be a negative value for it to indicate that it's exothermic in this process. So again, sometimes people have a hard time with that aspect of it. It is the same numerical value. The difference here is the sign. Although you may think the sign is not really important, it does indicate a lot in terms of what's happening with that energy. Is it going to be endothermic or exothermic? And again, endothermic always, when you're talking about heat and energy, is a positive value, while our exothermic is always a negative value when we look at it. Now, the stronger the bond, the higher the bond energy is, and the higher the bond energy, that means it is harder to, again, the higher the bond energy, it's harder to break that bond. So we will want to stay together. So here's basically a bond. If we look down here at the bottom, these are all bonds between hydrogen and our halogens. So this is basically going down group 7, fluorine, chlorine, bromine, and iodine. So if you go to group 7, that's going down the group. On the periodic table. And when we go down group 7, what we see in terms of the bond energy is at the very bottom, it's only 71 kilocalories, for example, to break this bond between the hydrogen and the iodine. While as we go upwards here to the fluorine and the hydrogen, it's 136 kilocalories to break that bond. So up here at the hydrogen and fluorine, it's actually going to be a much stronger bond than what we see down here. And this has a lot to do with a lot of aspects of sort of chemistry. These are also, all 4 of these guys are also acids. And if you remember acids, I think we talked just a little bit about what acids were, but acids really are things that have the ability to produce H plus ions in solution. And in order to produce H plus ions, what would have to happen in each of these cases is you would need to break that bond between hydrogen and whatever it may be attached to, the I, the Br, the Cl, the F. And what we see in terms of bond energy is it's much harder to break that HF bond than it is at the HI sign. And what that means is in terms of acids, for example, these guys coming this way, this would be your strongest acid. This would be kind of your next strongest. This would be your next strongest. And then this guy over here, HF, is actually a weak acid. And it all has to do with really the bond strength. So the idea is in order for something to be an acid, it has to release that H plus or that H. And because this guy is the weakest in terms of bond energy, it means that this H, for example, will come off a lot easier than the H over here that we see. Because this guy is about 100, 60 kilojoules or kilocalories, 70 kilocalories more energy is required to break the bond in HF than you have in HI. Thus, what's going to happen is this HF bond is going to stay together a lot longer, and it's going to release less H plus into the solution. So that's why something like HI is actually a strong acid versus HF is more of a weak acid because of this bond energy. The strength of that HF bond is relatively strong. It's going to keep that H from coming off and making it a weaker acid than something like HI, where there's not a lot of energy needed per se to break that bond, and it's going to allow that H to come off a lot easier. So the delta H indicates the relative strengths of the bonds that are being broken and formed. Again, as I mentioned, when the delta H value is negative, that means more energy is being released in forming the bonds than in breaking the bonds, especially when you talk about bond energy. So if we look at this chemical reaction here, the bonds forming the products are stronger than the bonds broken. in the reactants. And overall, what happens in this reaction is that there is minus 213 kilojoules per mole of heat that's being released. We know this is exothermic and heat is being released simply because of that negative sign that we see there. And again, basically to figure out the delta H for the reaction, and if you're using what is known as bond energy to do that, you essentially take all the bonds, the delta H's for all the bonds that are broken, and you basically add it to the delta H for all the bonds that were made. And again, remember that all the bonds on our reactant side here need to be broken. While all of our bonds on the product side need to be made. And what that means when we talk about broken and made is, right, when we break bonds, it's an endothermic process. So when you add up all of those bonds together, it should end up being a positive number. While when you make all those guys on the product side, it's exothermic. So it should be negative number. And you would basically just add those two numbers together after you change one to positive and one to negative. You would find all these things based on all the bonds that you're making and breaking. So we're not probably going to do any type of calculation with it, but just to give you an idea as to, you know, for example, in this particular one here, when we talk about, you know, all these bonds that are being broken, for example, if you drew the Lewis structure for CH4, it would look something like this. And if you drew the Lewis structure for oxygen, it would look something like this. And if you just keep an accounting of everything that's happening, there's, in terms of the bonds that you're breaking on the reactant side, you'd be breaking 1, 2, 3, 4 carbon hydrogen single bonds. And when you would go to a table, that's where you could find the values for each of those. It'll say, hey, to break the carbon hydrogen bond, it's 200 kilojoules or something like that. You would also be breaking 1 and 2 because of the coefficient that we see here. There's actually 2 oxygen molecules that you would be breaking. And you would go to the table and you would find the value that's required, not to break the oxygen-oxygen single bond, in this case, it would actually be the oxygen-oxygen double bond. And again, you would add up all that energy. And that's basically the energy that's required to break all those bonds. And again, that would overall be a positive number because it's endothermic. And then on the product side, you would do the same thing. You would, if you weren't sure what it looked like, it's a good idea to draw it. So if you drew CO2, it would look something like this. And water would look something like this. And again, if you look in the equation on the bottom, the coefficient in front of water is not 1, but it's actually 2, which means you actually would have 2 of these guys that would be being made. And essentially on the product side, you would go to that table that would give you those values. And again, I don't anticipate us doing that, but on this side, you would see that you made not 1, but you made 2 carbon-carbon. Again, not single bonds in this case. You would want to look up the double bond value. While over here, you made 1, 2, 3, and 4 oxygen, hydrogen single bonds, which again would also have a value. And just like we talked about before, our making is going to be exothermic. So when you add up all those numbers together, should end up as a negative number, as opposed to down here where it's a positive number. And then basically you add all those numbers together, and that's essentially how they get to this overall value that is there. So when we talk about sort of energy based on bond energy or delta H value based on bond energy, it really is just sort of like an accounting of all the bonds that you broke on the reactive side, plus all the bonds that you made on the product side, and again, making one positive and one negative, depending on making or breaking. And you can basically figure out the delta H for the overall reaction. So really what this means overall, the energy associated with the product side is greater in terms of making those bonds than the energy associated with our reactant side of breaking those bonds. And we get a net of minus 213 kilocalories in this case that is being released as this process occurs. Any questions on that? And again, I don't think we're going to do any of those calculations, but in case you come across it somewhere, again, that's essentially how you do it. I always recommend that if you're not sure what these things look like, to sort of draw them out like I did, up here in this sort of example. And that allows you to sort of visually see what bonds you're making and which bonds you're breaking. And you also can visually see, is it a sort of single bond, a double bond, or a triple bond? Because if you do find that table or see a table like that, there will be different values in that table, if it's a double, single, or triple bond. Again, as we talked about, our triple bond is our strongest in terms of energy to break. Again, because when you make that, everybody's closer together every time you put on a bond, and our single bond is the weakest in terms of energy to break it. And the opposite is true here. If the reactants require more energy to break these bonds than it does to make the bonds on our product side, what we'll end up getting here is a positive value for the delta H for that reaction, which again means that it's a overall endothermic process. So overall energy is being absorbed. You would do basically the same thing. I'm not going to draw it, but again, you could, in this case, figure out how many bonds you're breaking, add up all the energy required to do that. And when you draw, say, like the Lewis structure on the right-hand side, you can figure out every individual bond that you got that's being made, add up all those numbers. And in this particular case, the net reaction is actually going to be endothermic or positive. And really, the simplest way to figure out, again, endothermic or exothermic, you could really care less about the number. But again, it is the sign that we see. So in this particular one here, it is a positive value, which means it's endothermic. While in the previous example, it was a negative value, which means that it is a exothermic process. And here's a little table that sort of summarizes what we were just talking about here. So what we have is our endothermic process basically means heat is going to be absorbed. And it also means that when we think about things like delta H, it's going to be a positive value. Other ways that we sometimes can represent heat and energy is with, as we'll see in a later chapter, Q, which means heat, will also be a positive number. And Q is sometimes used to represent heat, and it also will be positive. And when we talk about sort of bonds being made and broken, the bonds broken in the reactants are stronger than the bonds formed in the products. And what that essentially means is, again, when we break those bonds, it's endothermic. So the total value to break all the bonds is going to be larger than the value that's negative when we make all the bonds. The products are higher in energy than the reactants, and vice versa here for our exothermic. Again, heat is going to be released. Delta H will be negative. Also, when we calculate Q, which is heat as well, will be a negative value as well. And in terms of making and breaking, we would have stronger bonds being made than what was broken, which means our negative value would be there. And the products are lower in energy than the reactants. As we'll see in just a second, that's also one way you could determine sort of exothermic and endothermic, is sort of where the energy of the reactants and the products end up. I think we have some diagrams coming up that we will be able to see that. So let's talk about sort of those energy diagrams. So one way that we can sort of represent the energy change in a reaction is by using energy diagrams. And for a reaction to occur, again, a couple of things do have to happen. They do need to basically come in contact with each other. So molecules do need to collide for a reaction to take place, but they also need to collide with enough energy basically to get the reaction to take place. So for example, our AB here, this bond needs to be broken, and then the new bond between C and B here need to be formed as we see. The orientation is also important. So there's really two really important things in order for sort of a reaction to occur. One thing is obviously collision, so they do need to come in contact with each other. And when they do come in contact with each other, that's going to allow the reaction hopefully to take place. But they also need to come in contact with each other in the right orientation. So, for example, on the bottom here, this is sort of the correct orientation. For example, C is going to come in contact with B here, and that will sort of kick off that reaction to take place and that bond being broken. Now, if on the other hand, C came in contact with A, this would be sort of the wrong orientation for this reaction to take place, and we actually would not get a reaction to occur. So just because a collision occurs between two molecules, it does not necessarily mean that products would be formed. Those two important things has to sort of happen for a reaction to occur. It has to be the correct orientation in terms of those collisions. And in terms of energy, it's also really important. They do need to come together with a correct amount of energy to really sort of kick off that reaction, get that reaction to basically start. So orientation energy is really important for an actual product to be made in a reaction. Again, not all collisions will result in product formation. So this is what is sometimes referred to as a energy diagram, and an energy diagram has a couple of things. First off, we have our reactants that are there. So here's our reactants. We also have our products. And basically, as this reaction occurs, excuse me, we have a collision that occurs between, again, our C and our B. Is going to try to kick off our A. And as this happens, what happens is these guys has to sort of, these reactants has to climb this hill. And it has to climb this hill basically to get to the other side. And this hill, as you can see here, is what is known as E of A. And E of A is what is known as the activation energy. And the activation energy is that minimum amount of energy that's required for a reaction to occur. So the activation energy is really that when we talk about there has to be sort of a minimum amount of energy required for that reaction to take place, that is essentially your activation energy. So that's your minimum amount of energy basically needed for a reaction to occur. And it's basically, as you can kind of see in this picture, sort of that hill that the reactants has to climb to get to the other side. So this hill is what those reactants got to climb to get to the other side. And when we get to the very top of the hill here, that is what is sometimes referred to as the transition state. And what we end up having at the very top of the hill is, I'll just kind of make a little symbol. I'll do A and B. I'm going to do C as well. Put this like little symbol up here. And what we essentially have when we get up at the very top is sometimes what is referred to as a transition state complex. Or it's sometimes referred to as an activated complex. But it's one of those two things, either an activated complex or sometimes people refer to it as a transition state complex. And basically, what you have at that point, if you sort of think about what's occurring, is basically as the reactants go from our reactant side up this hill to the other side, we have to break all those bonds and start making some new bonds. So what you have sort of at this transition state is a place where we have bonds that are partially made, and we got some bonds that are partially broken. So in this particular example, as we approach the top of the hill there, the bond between A and B is starting to be broken, while the new bond between B and C is starting to be formed. And this is what is referred to as a transition state complex. And then what usually will happen is it will come down the other side of the hill, relatively quickly as it sort of proceeds down. So as we get to there, as it comes back down the hill to our products, it will sort of occur relatively quickly. And that is because this guy here, if you look at the diagram, this sort of transition state at the very top, this guy where we have sort of partially made bonds, we have bonds that are partially broken between all those guys. This is very high in energy, and things in high energy are not very stable. So they don't hang around very long. They're very high in energy, and they sort of very quickly kind of come down that hill, from the top of the hill and then come down relatively quickly. Usually transition states are very hard. Transition state complexes are very hard to isolate for that reason. They really don't hang around a very long time because they got this weird state of partially made bonds, partially broken bonds. They're extremely high in energy, which means they're not so stable. They just really want to get to the other side relatively quickly. So this is sort of what a classic sort of energy diagram looks like. We have energy on the left-hand side. This is sort of the reaction progression happening here. We're going in this direction, going from reactants to products in this case. And the other thing that we could see from this is when we take the difference between where our reactants started and where our products ended, this difference is that delta H, or that change in enthalpy for this reaction. So the difference between basically the delta H is our difference between the delta H of our products, which is where we ended up, minus our delta H of our reactants, where we started basically in terms of energy. And again, we're not going to really get into those calculations, but you can actually calculate these values and so forth. And if you did in this particular case, or if you look at this diagram, really the only two things that you need to look at to determine if this thing is going to be a endothermic or exothermic process in this case is where we see our reactants versus where we see our products in terms of energy. So let's draw it over here. Our reactants are here in terms of energy. And when we're all done with this reaction, our products are down here in terms of energy. So in this case, energy has come down as we go from reactants to products. And the only way for energy to go down as you go from reactants to products is energy needs to be given off to do so, right? So to get our reactants down to our products, we need to give off that energy. So energy is given off. When energy is given off, that's another way to say that energy is being released. And what that means is very badly here. It's not working very well today. Energy is released. That means that this process, whenever you see an energy diagram, that the reactants are higher in energy than the products, it is always going to be a exothermic process. And what that means, based on our conversation before, if we calculate the delta H for this reaction, regardless of what the number will be, that number should end up being a negative number. So this reaction should overall be negative, because what we see here is our reactants are higher in energy than our products. Again, in order to get down there in terms of energy, we have to give off that energy, which is a exothermic process. Any questions on that? So as I mentioned, the E of A is the activation energy. Again, it's that minimum amount of energy required for that reaction to take place. It is that hill that they have to climb to get to the other side. It also determines, in terms of reactions, how fast the reaction will occur. So for example, if that hill that you have looks like this, where this would be our activation energy, versus if you had that hill that looked like this, made that really small. When we compare these two, if these are our reactants over here, these are our products, our reactants, and our products, what we could see is it would take a lot longer for this reaction to occur, because these guys have to climb this really big hill that I drew here. So in order for this reaction to occur, these reactants has to climb this big hill to get to the other side. And this reaction over here, where I definitely went a lot smaller, a little extreme smaller, only has to climb basically this smaller hill. So when you think about how fast the reaction occurs, which is sometimes what is referred to as the rate of a reaction, the rate of a reaction is determined really by the activation energy. So the larger the hill, the slower the reaction would be, compared to somebody that had a activation energy that was smaller. You would expect that reaction to occur faster. Again, it's just a process where those reactants don't have to climb as big a hill to get to the other side. It's kind of like if you went for a walk, right, and you had to go up a hill. The bigger the hill, right, the longer it's going to take you to get to the top, and then maybe come back down the hill on the other side. Versus if you just had a very small hill, you could get to it a lot quicker to the top, and then you would get to the other side a lot quicker. So the activation energy does have a big effect in terms of reaction rates, how fast or slow a reaction will occur. Again, that higher one. What it also means is kind of like the example of people are walking. If you're walking down the road and all of a sudden in front of you, you see this big giant hill, you might decide, I don't really want to walk that big hill to get to the other side. But there will be a lot of people that'll go, nah, it's not a problem. I'll just go up the hill and walk to get to the other side. And that actually happens sort of in reactions as well. When we get that sort of big hill, that big activation energy, there may only be a few molecules willing to go up and over to the other side, or have enough energy to get to the other side. And that reaction, again, would probably occur a lot slower, because you don't have as many reactants getting up and over to the other side. Vice versa, if you're walking down the road, like I said, and it's just like, it's just this little bump in the road, most people will just, continue on to the other side, right? It's not a big deal. It's just a little kind of speed bump. For example, if you're walking down the street and you're going over a speed bump, it's not a big deal. Most people just continue to walk up and over the speed bump, get to the other side, have enough energy to do that again, rather than if you have this big giant hill in your way. Some people will turn around, go the other way, perhaps, and not go up the hill. And the same idea is here. If our activation energy is relatively small, we'll get a lot more people or molecules having enough energy basically to get to the other side. And when they do have enough energy to get to the other side, that usually will mean that the reaction will occur a lot faster because, it doesn't take as much energy basically to complete. And again, that difference between reactants and products is how we calculate the delta H of the reaction. Again, if we look at this energy diagram here, we see the same things that we've been talking about. Our reactants are higher in energy than our products. So again, the way you can just easily think about that is, in order for this reaction to take place, to get down to our products, energy has to be released, right? So that automatically should in your head tell you exothermic reaction. And the way you could verify that, again, if you did the calculation, what we see is our negative number there to tell us that it is a exothermic reaction. Now, this one, if we look at this, is also a energy diagram. We also have our reactants and we have our products, but this one looks a little different than the other two that we saw previously. The key here is what we see is our reactants are actually lower in energy than our products. Our products are actually going to be here higher in energy. And this is opposite of what we saw earlier. Whenever you have a energy diagram where you see your reactants are lower in energy than your products, the way you want to think about it is, in order for our reactants to get up there in terms of energy, energy has to be absorbed. Kind of help everybody get up and over. And when they get absorbed, what that should tell you is it's going to be positive. And this is your classic energy diagram for an endothermic reaction. So if you see an energy diagram where the reactants are lower in energy than the products, it's always going to be a endothermic reaction. We have all the same components as the other graph. We have our reactants. Again, we have this hill that the reactants has to climb to get to the other side. We also have at the very top our transition state, where we will have that guy where we have bonds that are starting to be broken and bonds that are starting to be made. And again, as you can see, it's at the peak of energy, also the highest part there, where we would have, again, that activated complex or that transition state complex. And again, activated complex is another way that's sometimes referred to. It's the same thing as the transition state complex that we were just talking about in the previous slide. And again, that's your guy with your partially made bonds, partially broken bonds. And again, because that is high in energy, it will relatively quickly drop down to our other side here, where we have our products that are being made in this case. And again, it's going to be a endothermic process, and this is the key of how to recognize that reactants lower in energy than our products. Any questions on that? You'll also perhaps notice a difference when we talk about our activation energy. So for example, let's just go back to here. Maybe go back to that first one. That's the same one, I guess. So here in our exothermic reaction, this is our activation energy in terms of this hill. When we look at our endothermic process, this is our hill that happens from our reactants to our top of the hill, and that's our activation energy. And that is typically what you will see when you compare your exothermic, where your reactants are higher in energy than your products. Your activation energy that you get when you do that is typically smaller than what you get when you do your endothermic process here in this really badly drawn one here, where our activation energy is here. So usually an endothermic process will have a higher activation energy than an exothermic process. And that sort of makes sense, right? Because in an endothermic process, heat and energy overall needs to be put in. And it needs to be put in to help everybody get up and over this hill to the other side. While in an exothermic process, because it has such a relatively smaller activation energy, it has enough energy most of the time for those guys to get up and over to the other side. And again, that bigger hill that you see will require the rate of the reaction to probably be slower. So in comparison here of our exothermic to our endothermic hill, we had to compare and take an estimate on the rate of that reaction. We would expect the rate of their exothermic reaction to occur faster, again, because of the smaller hill, than our endothermic process, where we have a larger activation energy, and we would expect it to take longer basically to get to the other side. Any questions on energy diagrams there? So let's talk a little bit about reaction rates there and how concentration, temperature sort of affect how fast or slow a reaction occurs. So when we increase the concentration of our reactants, so again, remember that in a reaction, right, we go from our reactants to our products, basically. And as this reaction occurs, and I don't hit something, if we increase the concentration of the reactants here, so if we increase the concentration, when you see this little bracket, it usually means concentration. And as we'll talk about in a later chapter, when we talk about concentration, it is usually molarity that we talk about, which is moles per liter. And we haven't talked about that officially yet, but that is usually what you'll see. Maybe if you remember from labs that you've done previously in person, the reagents or the bottles that you use for some experiments maybe had a number with a big M next to it, and that big M is the molarity or the concentration. Higher that number is in terms of M, the stronger it is. The smaller the big M number is, the weaker or more dilute that solution may be. But if we talk about sort of a reaction where, say, we have A plus B goes to make A and B, for example, right? If we increase the concentration of our reactants, that typically will increase the reaction rate. Because remember, there's two things that has to occur, right, for a reaction to take place. You need to have a collision. And these collisions do need to be in the right orientation, as we talked about earlier, and we do need to collide with the right amount of energy. So one way to sort of help us with this part of that, the collision part, is if we increase the concentration, that means there will be more reactants available. So more of these guys available, floating around, say in a solution, whatever it may be. And because there's more of them available, that should lead to more collisions occurring between them. And more collisions should occur in more correct collisions in terms of orientation. And that should also allow us to start to make more product in this case. So it should increase the reaction rate. The opposite is true as well. If you decrease the concentration, If you happen to do the opposite and decrease it, so I'll put plus here, plus here. Like if we increase it in the blue there by adding them. If we decrease it, I'll go with red. Let's say, well, I'll just use negative. If we sort of take away these guys or lower the concentration, that's going to have the opposite effect on the rate. If we lower the concentration, that means there's less of those A and B, for example, there in the solution. That means it's going to take longer for them to find each other. The longer it takes for them to find each other, the lower the collision rate will occur, and thus the rate of that reaction will decrease as well. So one way that you could sort of affect the reaction rate in sort of both ways is if you increase the concentration, that should supply more collisions, and that should see an increase in the rate of the reaction. And vice versa, if you somehow removed or took away concentration or lowered the concentration of the reactants, that would require a lot more time for them to come together, and that should lower the rate of the reaction. Temperature also has an effect on the reaction, and what temperature affects is sort of the second part that's necessary for a reaction to occur, and that's energy. So when we increase the temperature of a reaction, that means that our reactants here, A and B, now have perhaps more energy than they would normally have. And when they have more energy, they will be able to hit that activation energy, basically. They'll have enough energy to take themselves up that hill to get to the other side. And you would have more reactants able to do that. So since these guys have now gained energy by increasing the temperature, you have more reactants able to get up and over the hill to the other side, and that's going to increase the rate of that reaction, again, because everybody has enough energy to get up there. In addition to temperature could also help with this, the collisions, because as they increase energy, they're going to be moving around a lot faster probably, and thus the collision rate would also probably go up as well, in addition to those guys also now having the correct amount of energy to get up that activation energy to the other side. The opposite is true as well. If we do the opposite of that and we decrease the temperature, we bring the temperature down, the opposite effect occurs. Basically, now everybody has less energy, and they're not going to be moving around as fast, which means less collisions. They also, when they do collide, may not at that point have enough energy to get up and over that hill to the other side. And what you will typically see is the rate will start to decrease as well. So if you drop that temperature, usually the rate will go down. And vice versa, if you sort of increase the temperature, that rate typically will increase as well. So two really big sort of factors that affect how fast or slow a reaction occurs is rate, again, is temperature. If you increase it, the rate typically increases. If you lower the temperature, the rate usually decreases. So for example, every sort of a general rule is every 10 degrees Celsius that you raise the temperature for a lot of reactions, that's enough to basically double the rate of how fast that reaction occurs. Not 100% of the reactions, but usually it'll double the rate of a lot of reactions. So concentration and temperature are really important in terms of how fast or slow a reaction will occur. And that is really what we were talking about when we talk about rates of reactions. It's basically how fast or slow a reaction will occur. Another very common way that you can kind of speed up a reaction, you technically could also lower it this way as well. But in most cases, when people talk about a catalyst is basically a substance that will speed up a reaction. And a lot of times in equations, when you see the arrow, you'll sometimes see things written on top of the arrow, something like platinum, like we see here, or palladium. Sometimes you'll even see something like H plus written up on top. H plus sometimes refers to it being an acidic catalyst, or an acid is being used as a catalyst. But a catalyst is typically something that will basically speed up a chemical reaction. And a catalyst, though, a couple important things about a catalyst is it's not considered a reactant. So it's not a reactant. So it's not considered a reactant. It's really not considered a product either. So we don't consider a catalyst a product as well. It's actually, as it says, not even used up in the reaction. So it's actually still there when the reaction's over. Its sole job usually is to speed up a chemical reaction. And it can do that in many different ways. There's catalysts that basically just allow the reactants to come together more efficiently. It could be a solid place where both reactants are attracted to, and it sort of allows them to naturally sort of come together a lot quicker than if the catalyst wasn't there and they're just kind of moving around trying to find each other. So it really is just sort of there to speed up the reaction. How is it able to do that? It's able to do that if we sort of go back to our energy diagrams. Again, we have that hill that we have to climb to get to the other side, for example, between our reactants and products. Again, that's going to be your, not right there, try it again. Good thing they made erasers, I suppose. There we go. So this is going to be your activation energy here in this reaction that is uncatalyzed. Now, if you add a catalyst to a reaction, what it will essentially do is lower the activation energy. So instead of this guy having to go way up there, perhaps it cuts it down to here. And in this particular case, I'll draw it off to the side. It should be to the center, but got something else there. This is the activation energy. So these reactants only have to climb the hill over here that's blue to get to the other side, which is a much smaller hill than they did in the red hill in the uncatalyzed reaction. And because they now have a much smaller hill to climb to get to the other side, there will be a greater majority of reactants that can do that, that have the sufficient amount of energy to get to the other side. And again, because they're only climbing this smaller hill to get to the other side, they will get to that other side faster. And when they get to the other side faster, that means that the reaction rate will be a lot faster than the uncatalyzed reaction. So that is essentially how a catalyst works. It lowers the activation energy. And because it lowers that activation energy, the reactants have a much smaller hill to get to the other side. That means more reactants are able to do that. That means an increase in the rate of the reaction versus the uncatalyzed reaction. Any questions on that there? And that's what we see, maybe a much prettier picture here, but our catalyzed reaction here in red, our uncatalyzed here in blue. Again, the uncatalyzed reaction, a much bigger activation energy than our catalyzed reaction. Thus, those reactants can get to the other side a lot quicker and a much higher rate of reaction than we see in the uncatalyzed reaction. And again, it is not a product or a reactant. Really, catalysts are just there basically to facilitate a more efficient way for everybody to get to the other side. Kind of like the old, was that Roadrunner cartoon with Wile E. Coyote and all those kind of things, right? So, instead of going up and over the hill to get to the other side, it's like the Roadrunner, right? Finds the little trap door in the hill and he just goes straight through the hill to get to the other side. and instead of going up and over, and then obviously you get to the other side a lot quicker. And that's essentially what a catalyst does, is just able to sort of find an alternative pathway. Same thing happens in our body, right, with proteins, enzymes. Again, it allows a more efficient way for these things to come together. In terms of enzyme and proteins, there's usually an active site, sort of the same idea. You have to have the right orientation. You also have to have a collision that occurs in order for these guys basically to come together in sort of that enzyme substrate. Any questions on rates of reactions, catalysts, speeding up reactions, slowing down reactions? Again, just to sort of summarize, the rate of the reaction is determined really by two big things. It is the collisions and the energy. And the greater the concentration of reactants, the greater chance there's going to be collisions and more guys with the right amount of energy to get up and over to the other side. While, again, the lower the concentration, it's going to take longer for those collisions to occur. And again, the reaction rate will slow down. When you increase the temperature, again, as we talked about, gives everybody more energy to get to the other side, and vice versa. If you lower the temperature, less energy. And again, another way that you could kind of usually speed up a chemical reaction is to add a catalyst, which again is there to simply facilitate the reaction occurring faster by lowering the activation energy. Any questions on any of that stuff there? All right, so the next thing we're going to talk about is equilibrium. And equilibrium occurs with a certain type of reaction, and the way that you can sort of recognize it is right here. When we look at the equation, we typically will see reactions that are heading in both directions. Right? So this is our reactants on this side and our products on this side. And basically, a reversible reaction is different than a non-reversible reaction. Most reactions or equations that you see have basically an arrow only heading from reactants to products. It's kind of a one-way street, if you want to think about it that way. While this way is really a two-way street. So in a reversible reactions, unlike in a non-reversible reaction, reactants will go to products. At some point, once you start building up enough products, these guys will actually start heading in the opposite direction. Their products will go and start making our reactants again. And this will continue in this process where reactants are being made to products and products coming back the other way. This will continue to happen until what is reached is known as chemical equilibrium. Now, chemical equilibrium, just so we're clear about what that means, is very common. People think it means that when we reach equilibrium or when we reach chemical equilibrium, if I spelled it right there with a U. Sorry about that here, equilibrium. When we reach chemical equilibrium, it does not necessarily mean that we have the same number of reactants and products. It doesn't mean that their concentrations are the same. It does not necessarily mean that. When somebody says that this reaction has reached equilibrium, what they are actually referring to is the rate of the forward reaction will equal the rate of the reverse reaction. So the rate of the forward reaction, and in the forward direction, that is going from reactants to products, will eventually equal the rate of the reverse reaction. The reverse reaction is going from products to reactants. And what that means is the rate of each of those things are equal to each other. It doesn't mean that the concentrations are equal to each other. So what that means is, for example, and again, I'm just making up these numbers. let's say that this reaction here that we have in the center of the screen reaches equilibrium. What that means is, let's just say at that moment when it reaches equilibrium, the concentration of CO was 4, the concentration of H2O was 2. Again, just making up these numbers. The CO2 was 3, and maybe this guy was 4 or something, for example. What we see is it doesn't necessarily mean that we have the exact same amount on both sides. What it means is, because as quickly as it goes from left to right, is going to just as quickly head back in the other way. What that means is, when you look at their concentrations, they pretty much will not change. And what we mean by that is they won't change from where they're at that moment. So when they reach equilibrium, for example, here, the CO will continue to stay at 4. The H2O will continue to stay at 2. The CO2 will continue to stay at 3. And the H2 will continue to stay at 4 as well, because just as fast as they go to the right, they're just as quickly going back to the left. So what that essentially does is, when something reaches chemical equilibrium, it locks everybody into place as to where their concentration is at that particular moment. So again, very wrongly, sometimes people think it means, okay, it reached equilibrium, that means we have the same amount on both sides. And it doesn't mean that. It just means that as it's going to the right and as it's going to the left, that is occurring at the exact same rate, and that will lock everybody into place. And what that means is, visually, if you had a beaker in front of you where a reaction has reached equilibrium, it may look to you like there's not much going on. Perhaps the color has changed and it just sits there now, say colorless, for example. And it may look to you, if you're just looking at this beaker, like it started out as red and now it's colorless, and it's been colorless now for a long period of time. There's not much going on. It has reached equilibrium. And visually to you, it may look like that. But if you were able to sort of super zoom in on sort of what's happening on the molecular level, you would see a lot of activity, because it just means that this reaction is going this way really quick, it's going this way just as quick, and there's a lot of activity continuing to occur. If you super zoomed in on the molecular level, it's going from reactants to products, products to reactants, occurring at the same rate. But although visually, if you sort of zoom out, if you will, and look at it on the big scale, to you, it may look like nothing much is happening. There's like static is sometimes referred to, not much going on. But again, if you really got down to the molecular level, there's a tremendous amount of activity happening to maintain that equilibrium, going forward and going reverse. So chemical equilibrium, again, means that we don't necessarily have exactly the same amount on both sides in terms of reactants and products. What it is actually referring to is how fast the reaction is heading from reactants to products, and how fast it's heading from products back to reactants. And when we do reach that equilibrium, that means that you have this situation occurring. The rate of that forward reaction will equal the rate of the reverse reaction. Any questions on that or anything that we talked about here today? So I think we're going to stop here. Is probably a good place to stop. We're almost near halfway through here, or more, of this chapter. Again, a couple reminders. This coming Wednesday, which I guess would be the 22nd, we will be having a quiz. We will also be lecturing, so we will start lecture at our normal time of 7:35. We're probably going to stop early, so maybe 8:30, maybe a little before, and then the quiz will be available for you to take. Again, I don't anticipate it being a super long quiz or anything like that. It is based on only nomenclature, so all the nomenclature from, I think a majority of it was chapter 3, but there was a little bit in chapter 4. We sort of did all the nomenclature together in the notes, but it is made up of basically 3 and 4. But just the nomenclature part, none of the Lewis structure part or bonding part, just the nomenclature part. And that includes all of it: type 1, type 2, type 3, polyatomic ions. And again, I think we talked about acids as well, so that as well. And so around 8:30ish, it should be available probably for you to take, and then we'll be done with lecture about that point, and you could go take it and probably still be okay for lab, I would think, if you took it kind of right away. You do need to know, again, the polyatomic ions, that is writing formulas correctly, naming things correctly, and all those type of guys. Then 1 week from Wednesday, which again I think would be the 29th, if I'm doing the math there right, is we'll take our exam number 2 up on Canvas like we took our first one. And again, that will cover chapters. It should be 3, 4, and 5. Again, 5, the lectures are online if you haven't seen them or didn't see those announcements. Hopefully you did. So I'm just going to move the exam 1 week just to give everybody a little bit of time to catch up, just in case you didn't see those lectures. So you want to make sure you look through them. And if you do have questions, make sure you do contact me. I'll be happy to answer that. The homework is going to be moved. I just haven't had a chance to move it, so I'm going to move it to next week as well. So I just haven't had a chance to do it. In the next day or so, I probably will move the homework to the following week as well, like with the exam. You will not be provided the polyatomic ion names. You do need to know those guys. So again, the chart that we saw, you do need to be familiar with the polyatomic ions. You will be provided a periodic table on the quiz, obviously, so you can look at it where everybody is in terms of groups, but you do need to know those guys' names. Any other questions? That goes for both the quiz and the exam as well. Okay, I think that's all the business, if I'm not mistaken. All right, so again, there will be a lecture on Wednesday. We're just going to stop early, and again, that should free up some time for you to take the quiz and get it out of the way and not have to worry about sort of lab interference or anything like that. All right. So other than that, I'll see you on Wednesday. And again, quiz on Wednesday, exam 1 week from Wednesday. And then we'll just continue on. Have a good rest of your day. And I'll see you on Wednesday. Thank you.